Yeah, it's on time. Got it. Okay. I guess we've got a few people coming. There are a couple more to do. Okay, so my name is Peter Hartley. I'm the Peterkin Professor of Economics at Rice University in Houston, Texas. And I'm one of the co-directors of the Master of Energy Economics program at Rice. And I also have quite a few PhD students working on energy economics issues. So anyone who's online who would like to come to Rice to do PhD in energy economics, you're most welcome. But I'm right at the moment sitting in University of Western Australia in Perth. And that's a West Australian beach behind me. Anyway, we have three papers today from three people speaking about oil markets mainly. Well, I guess one of them is more general. It's energy demand elasticities. We're going to spend 30 minutes on each paper. So our first speaker is Esti Widyastuti from the University of Aberdeen. I'm sorry if I didn't quite get your surname correct.
Okay.
But she's originally from Indonesia, and she's going to talk about oil market uncertainty, which is a new measure of uncertainty, and uses that measure to investigate some relationships between oil market uncertainty and other oil market variables. So I'll hand over to you, Esti.
Thank you, Peter. All right. Okay. So good morning, everyone. Good morning from Aberdeen, Scotland. So my name is Esti. I'm from University of Aberdeen and joined program with Concurrent University Australia. And this work, this time, I have the opportunity to present my work together with my supervisor, Marc Gronwald, and he used to be in Aberdeen as well, but now he's in Xianjiaotong, Liverpool University, China. So today I would like to cover about the measure of oil market uncertainty with the application of Google Trends. So first part, I would like to talk about the recent contribution or the existing literature about the uncertainty in general. And so it covers the existing uncertainty indices. And then second one, I'm moving on to the application of Google Trends itself. But again, it's a bit more general in this side. And then next one, then I'm moving on to the specific one for GTU oil market to measure oil market uncertainty. And then at the end, I would like to compare between the newly proposed index with the existing benchmark indices, and then analyze the effect of the uncertainty on the global oil market variables. So first, the recent contributions, so the existing literature about uncertainty in general. We usually use OVX or VIX. It's the expected 30-day crude oil volatility index. So it's like a short-term volatility index. And then there was some work by Jurado and others. They proposed the macroeconomic uncertainty. So they applied the forecast of the conditional volatility for the macroeconomic or business cycle. And then afterward, there were some work from Baker and others. They proposed the economic policy uncertainty. Their work discussed about, not discussed, their work like proposed about the newspaper coverage frequency based, such as economic uncertainty or regulation. So basically, they try to find, they try to count how many words those specific terms, economic uncertainty and regulation, that frequently occurred on the newspaper. So the idea is like the more people are uncertain, the more those topics coming up to the newspaper. And then after the work of Baker, Davies extend their work by incorporating more countries. So that's why it came up with the global economic policy uncertainty. And then there were others like geopolitical risk uncertainty. Also the Caldera and Iacoviello, they apply similar concept with Baker and Davis, but then they specifically work on geopolitical. So they use such as the keywords such as tensions, military, and etc. And then word uncertainty index by Ahir, they use only one single basic word uncertainty in quarterly EIU country reports. So those were some work in general uncertainty in literature. So here we go. So these are all the time series of those indices. I started from 2008 just to make it easier to see the movement between one another's, because like OVX is the shorter period than other indices, but others, there are some that start from 60s, 70s, yeah. But this time I just want to show some peaks or from OVX. It has few peaks around 2008, 2009, and then 2015, 2016. And the last one was the highest in 2020. And it's quite similar with Jurado's macroeconomy index, JMU. I will just call it JMU later on, just to make it shorten. And also Jurado's has some few peaks as well, 2008, 2015, and 2020. And for global economic policy uncertainty, they have such kind of like increasing trend. Also, the highest was in 2020, but then also some other peaks, but relatively increasing trend. And GPR, geopolitical risk index, also exhibits similar movement and trend to the GEPU. And for word uncertainty index is a bit different, a bit less correlated, but also the highest to 2020. And also the data is low, using low frequency data. So that's why a bit showing not that intense, because as not as high frequency as others indices. So then we move on the application of Google Trends in the existing literature. So I just want to share a little bit description briefly about the Google Trends. So what is Google Trends? Is that part of Google that can give us the idea of the relative frequency between one specific search terms compared to the most famous search terms in that search platform. So for example, the maximum value of Google Trends, if we look at it, the maximum value is 100. So say the search term has 50 in terms of its value, then it means it's half popular compared to the most popular trending topics in that certain specific region and certain periods of time. And why do we utilize it? Because yeah, it's freely to access to everyone, and then like it's quite very easy to generate. It's just a bit similar with Google actually. Like we can just put the terms and then like it will show up the value, that how much the relative frequency for each term. So what current literature says about it? And first, Zielinski in 2012, the paper discussed about Google Trends by inputting only one single search term, economics. So they just put economics and then like generate the value for the US application. So they measure general economics indicator from Google Trends. And then Castelnuovo and Tran, their work most specifically work in macroeconomic uncertainty indicator for the scope of US and Australia. And Tran extended the work of Castelnuovo and Tran work specific for New Zealand scope region, and Bilgin for Turkey. But yeah, most of those literature discuss Google Trends with the application for macroeconomic or financial indicator. But specific for oil market, I just found some of the literature which are by Goji, that they see how the correlation between the Google search volumes, oil price, and other financial things and Libya like more into connecting the oil market to the geopolitical tension by taking example from Libya war. And then gak ada nama, but they use a single search term oil price in Google Trends to measure sentiment, investment sentiment indicator. And Lee et al. And others, they just use single terms as well, brand, to see the correlation with the oil price. So in this work, I extend the work of Castelnuovo for entrance procedure, but because they work in macroeconomic, and I would like to measure it for the global oil market specific uncertainty index. So this is just the general procedure how to obtain the Google Trends based uncertainty indices. So first we need to select the set of keywords. So because Castelnuovo Trends work in macroeconomy, so those are the examples that they take into account about the search terms. And aggregating monthly search terms into one index, because we can choose basically daily or monthly or yearly for the value of the Google Trends. And then for one round of Google Trends is just restricted to be just only 5 search terms. And so we need to make kind of like a rescale factoring between one and another round if we want to run more than one round. And benchmark term is important here because yeah, if we have 5 separate words, then we need one benchmark term to connect between one and each other from one round to another round. And then the final index, yeah, it will be our uncertainty index. So that's just the brief about how to generate it. And then now I'm moving on to the measure of oil market uncertainty. So this is the work that we are proposing. So we propose to capture different types of oil market uncertainty by using these components of the oil market. So first, oil investment, and then oil demand, oil supply, and oil market specific. So those are the search terms that I use to put into Google Trends. So for example, if I want to see Google Trends uncertainty index for oil investment, I put oil investment, oil exploration, oil project, and oil drilling. But because the maximum is 5, so the 5th one, I put oil price as the benchmark. And I would do the same for the oil demand, oil supply. So yeah, oil price is to connect between one and another indices. And oil market specific is the aggregate index for those 3: oil investment, oil demand, and oil supply. And I generated for worldwide scope and in a monthly frequency index. So here we are. So after I combine and aggregate all of those search terms into one final index, so these are our GTUs for oil market uncertainty. So basically they have similar peak, but for other movement, yeah, slightly different between one and another. But the big peaks, the major peaks are similar because we use the oil price as the benchmark to link between one and another. So the peak is around 2008, 2009, 2015, 2016, and 2020. 2020 is the highest one. So if we compare GTU, oil market specific, with the existing uncertainty benchmark, we can see that it shows a quite similar peak with the one from a short-term crude oil volatility index and Jurados. So again, around 2008, 2009, and then 2015, 2016, and 2020. And it's similar with Jurados. As well as for GEPU, actually, but just in here, 2015, GEPU doesn't really show the peak. But for 2008 and 2020, yeah, it also has the similar one. And for GPR and World Uncertainty Index, it doesn't, a bit like less correlated, but yeah, it's a bit makes sense because they use like totally completely different parameters. So here is the correlation between our GTU and the existing benchmark indices. So all have positive correlation except world uncertainty index, but yeah, because yeah, it used different parameter as I mentioned earlier. But for OVX, Jurados and GEPU, yeah, they show positive and quite high correlated with OVX and Jurados. And if we see the series over time with crude oil price, also we can see that in 2009, when oil price goes down, the uncertainty index GTU oil market goes up, and then oil price stays stable, quite high between 2010 and 2014, but GTU stays in quite low regime. And then GTU increases when oil price goes down in 2015, 2016. And at the end, 2020, GTU oil price goes down. Yeah, this is money data, but if we remember, there were some few days that WTI went into negative last year, and GTU goes up in 2020. Then we would like to see how does the GTU behavior affect the global oil market. So we would like to take into account oil price, of course, and then rig counts. Why rig counts? Because it's important indicator in exploration activity, and based on current literature that crude oil production has little to no response to oil price changes. So the one that has stronger relationship with oil price is the rig count. So that's why rig counts we took into account. Yeah, this is just the series over time for world rig counts and crude oil prices. And so we use the monthly data, January 2014 up to the latest one last month. I already updated the data and the estimation. In terms of methodology, we use the standard VAR model, and we run oil price, rig counts, and uncertainty indices. So we run a few equations for the uncertainty indices. We try to see the comparison between existing benchmark to global oil market, and then GTU to global oil market, and then impulse response analysis. So here we go. Rig counts responds negatively mostly to the existing benchmark OVX, Jurados, and GEPU. But OVX and Jurados, but GEPU, yeah, a little bit showing peak at some point. And GTU, it shows the same. So rig counts also responds negative to global to Google Trends uncertainty oil market specific index. And for oil price, it also shows negative response to Jurados index and as well as GTU. But for GEPU is not that clearly significant, the response of crude oil price on it. And yeah, so I just want to conclude that we try to do the application of Google Trends for specific oil market uncertainty, because not so many benchmark for specific oil market uncertainty in the current literature, except from short-term volatility index. And our proposed GTU index has a positive correlation with the existing benchmark indices. And then from empirical analysis, global oil market, which are oil rig counts and oil price, responds negatively to the uncertainty. And we can see that Google Trends-based uncertainty can be used as a new alternative index to measure public awareness on major events. So yeah, because the idea is when people are uncertain and then they intensify their search on Google. So yeah, that's all I think from me from my presentation today. So I look forward to any questions and comments. Thank you. So I will return it to Peter.
Thank you very much, Esti. You did a very good job on the time, very clear. Anyone from the audience who would like to ask a question, and we have quite a few people in the audience, please, you can type your questions in the chat. And I've got the chat open and I will be able to see those. In the meantime, I'm going to ask Esti a few questions I have myself. First one is as a clarifying question, two clarifying questions. When you said you had the oil price and everything, that was the mention of the oil price in Google Trends, right? Yeah.
Yeah.
Not the actual price, yeah. And then when you did the VARs, did you have one of these uncertainty indexes at a time in there, or you had multiple? So you tried
one
VAR with one index and the other variables, and then you just swapped them in and out?
Yeah.
Okay. Did you ever try, so it would seem that your index would be most closely correlated with the OVX, and in fact, your picture showed that. But did you ever sort of try if you like, a horse race? Where you compared how well your index worked compared with the OVX?
No, I haven't tried.
Okay. Because, I mean, it's one thing you could do is just to try to see. I mean, you showed us the results. I think the OVX is closest to your index, right? So I think it would be quite interesting to compare the performance of your index with the OVX much more. Can you give us some diagnostics on the fit of the VARs with the two alternatives, and maybe try some analysis where you include both your index and the OVX to see which one might.
Yeah, sure.
And in that regard, another thing I was thinking that you might try is you would expect, if your measure is a good, and given how closely correlated with this OVX, I'm sure it's going to work, but you would expect that the options price, the oil options prices should be very sensitive to uncertainty in the oil price. So that might be another thing to look at is how well your index explains changes in oil market options. And perhaps you could test OVX index in explaining options prices. Did you think about that?
Oh, I haven't. But yeah, it's a good point. So yeah, I will do the kind of like testing between those two, actually. OVX and GTU.
So I think the OVX is the obvious one. And then something else, you mentioned that you've got rig count.
Yeah.
Okay, so you've got the relationship between uncertainty and rig count. There's a couple of issues there. One is, because you think about exploration, you didn't have production. But I mean, some production can respond to the oil price, particularly Saudi Arabia's use of spare capacity, for example. There's a lot of evidence that responds. And then also with unconventional oil in the United States, sort of converting drilling uncompleted wells. So completing the uncompleted wells would be another thing which might respond. So those variables, you could also look whether the volatility index, but you might want to keep the price level in there as well. I mean, in your VARs, I don't know, did you have the oil price when you had the volatility measures and those VARs? Was the oil price in there as well?
Yes.
Or just the volatility?
Okay, can you clarify? So here,
in your VARs, what were the variables in your VAR?
Crude oil price, rig counts, and uncertainty.
So and you just had each of them in each time, or you had them all three in?
Yeah.
And the uncertainty measure?
Yeah.
Okay, so you had the price. Okay, you've got it. Okay, and then what did you say? The volatility measure, the price, rig counts, and what was the other one?
Rig counts, oil price, and that's all. Response to uncertainty.
Just rig count, oil price, and uncertainty. I see. Yeah. Okay. So I mean, another thing you might be able to get would be sort of inventories or something like that.
Oh, yeah. So
and like I
storage.
mentioned, and like I mentioned, Saudi, use of spare capacity, OPEC spare capacity, or
Capacity
like that.
utilization rate.
Yeah. And now, in your, I don't see any questions. I don't know if anyone has any questions. Again, if you have any questions, people from the floor, please type them in the chat. I noticed that when you categorized your variables as demand, what were they? Demand, supply, investment. Do you have different categories?
Yeah.
Normally, we would think, if you go back and look at these lists, if you look at these pictures, it's kind of interesting. I mean, your measure is very close to the OVX there, actually, on that page. Okay, and then on this one, actually, you could have included, you've got investment, demand, supply. So these are the indices you've got. They're the separate indices, right? Now, if you go back one page, if we go back one page, yeah, okay, there. So the other thing you might think of demand side, certainly recession, economic growth, global economy, industrial production. One would think of those as shift variables for the demand curve. On the supply side, on the supply uncertainty, on the other hand, you've got oil supply and oil production, which are kind of the two endogenous variables, right? Then shale oil and OPEC. I guess OPEC is OPEC production, is it? Not spare capacity.
Yeah.
What you don't have in there is a cost shock, I guess. So you might think of it like a shifter for the supply variable, like the others as shifters for the demand curve. And then I see. And then down the bottom, the oil market specific one, that's just the aggregate of the three. Yeah. Yes, that was my other suggestion, was the supply one. There might be kind of cost shifters, perhaps, like in the United States, you can get an oil factor cost. There's an oil cost of oil index.
Oil cost index.
Yeah,
so that's for the oil supply, right?
On the supply curve, yeah. Like a shifter for the supply curve, right? It's actually pretty closely related to the real oil price. And in all these cases, you included mention of oil price. That's good, yeah.
Could you please repeat once more about the one that I need to change in GTU oil demand? The word research term.
For oil demand, I'm okay with what you've got for oil demand.
Okay.
I think. Yeah, I was just thinking the supply one, oil supply and oil production. You think of those as reflecting both demand and supply.
Yeah.
Okay, I've got another question here from the floor. It's related to the storage point. Can you see the chat? Is there a criteria for choosing the terms in Google? Probably inventories may strengthen the index. Same with refinery utilization. That's some good suggestion.
Related to storage point, is there a criteria for choosing the terms in Google? Yeah, I think for storage, yeah. If we would like to add, yeah, we can think about the inventories, storage, and I think what I found in EIA website for storage, it's closely related to inventories and capacity utilization rate.
Yeah. But the bigger question is, why did you choose the different variables? Now I can see the demand ones, like I said, are shifting for the demand curve. The shifters for the demand curve, right? So logically, you think of the supply, you won't want to think of shifters for the supply curve, which is why I suggested costs. But But why you would have oil supply as a supply curve, but not oil demand and demand curve. And I guess the gap between those is inventories.
Yeah.
But okay, if anyone has any more questions. If not, we will move on to our next presentation.
Thank you, Peter.
Thank you very much. Thank you very much, Esti. Our next one is Yuko Hoshino.
Yes.
And she's studying energy price changes, the effect on household expenditure in Japan. So I'll hand over to Yuko.
Thank you, Peter. Yes. Hello to everyone. My name is Yuko Hoshino, and this research is collaborative study with Ms. Ogawa of IAEE. Thank you very much. This figure shows the CO2 emission by sector in 2019 in Japan, and household account for the 19% of Japan's total CO2 emission. And this figure shows the CO2 emission per household, and it peaked out at 2012, but however, it is not on the clear track of decreasing trend. And recently, carbon pricing is expected to be effective as a CO2 reduction measure in the household sector. And the effectiveness of carbon pricing depends on the price elasticity of energy demand. So this is our focus point. And in this picture, the black line, this picture shows the share of energy and transportation expenditure in the total household expenditure. So, and in this picture, black line shows the low-income household, and red line is high-income household. And yes, and from the figure, we can find out that when the oil price, and this dotted line is oil price. So when the oil price rise, the increase of black line is bigger, a little bit bigger than compared to the high-income household. So research question is price elasticity of energy demand in low-income household lower than in high-income household? If so, the price rise affects more on low-income household than high-income household. So in the following study, we estimate the price elasticity of household energy demand. So we focus on the household heterogeneities concerning the price elasticity. So as for the heterogeneities, we focus on income and city size differences. So this is the data we use in this analysis. And this figure shows energy expenditure data. So as for the energy expenditure data, we use the annual time series data aggregating the family income and expenditure survey, which conducted by the State Statistics Bureau. And total consumption expenditure of household is divided into 7 expenditures that are electricity, liquid petroleum gas, city gas, kerosene, gasoline, transportation expenses, and other expenditure. And other data, this figure is energy price data, but unfortunately, we cannot get the data of city gas from the same survey data. So instead, we use the national average of consumption price index for each item as for the price data. This figure shows the household income and city size distribution in Japan. And this figure shows the average household income by category. And there are 5 categories, income categories, and each category has an equal number of households. And this figure shows the income distribution in Japan. So these are the average income of each income category, household income categories. And this figure shows the number of households by city size. There are 4 types of city size: large, middle, small a, and small b. And large city means ordinance designed major city and including Tokyo metropolitan area. And other category is categorized by a number of people, number of population. And these figures are the share of energy and transportation expenditure in the total household expenditure. And this figure shows by household income, and this figure shows by city size. And in this figure, black line is the lowest families one, and the red line is the highest income families. And in this picture, this line blue line shows small city B, and this blue line shows large city. So from these data figures, we found that the share of energy and transportation expenses is increasing in low-income households and also in the small city. And on the other hand, in high-income household and large cities, and the number is relatively stable at around 8%. And this figure shows the expenditure share of each energy source and services by household income. And among them, the share of electricity expense is the largest in all income categories, this one. And as for the utility cost, such as electricity, city gas, LP gas, kerosene, the lower the household income, the higher the share of expenditure. So from this figure, it implies that the impacts of rising energy cost on the household energy consumption are different by the income category. And this figure shows the same thing by city size. So same as the previous slide, the share of electricity expense is the largest among them. And as for the city gas and transportation services, the larger the city size, the higher the share of expenditure. And on the other hand, the share of expenditure of electricity, LP gas, kerosene, and gasoline are higher in the small city compared to the large city. So this implies that the impacts of rising energy costs on the household energy consumption are different, and not only by the household income, but also by city size. And this figure shows household attributes by income category. And this figure shows the number of household members. And as you can see, the number of household members gradually decreasing, and this is the lowest household. So the lower the household income, the smaller the number of household members. And this figure shows age of a householder. The age of householder increases in category 1 and 2, this one. So the lower the household income, the older the age of householder. And this right figure shows household consumption expenditure. So consumption expenditure of high income household gradually decreasing, this red one. And on the other hand, that of low-income household is relatively stable during the period. And this figure shows the same thing by city size. And number of household members is as for the number of household members, the smaller the city size, this orange one is a small city B. Smaller the city size, the larger the household size. But the gap between them are narrowing gradually. And this picture is age of householder. So the age of householder increases in all city size, and the age of householder is almost same among the cities in different sizes. And this last picture shows household consumption expenditure, and this orange line shows the smaller city B. So the smaller the city size, smaller the household consumption expenditure. Okay, so and this is the model we use in this research. And in order to estimate the price elasticity of household demand, energy demand, we develop a trans-logarithmic model as follows. The share functions, there are 7 items that are electricity, LP gas, city gas, kerosene, gasoline, transportation services, and other consumption. And this WI denotes the expenditure share of the I's energy and transportation expenditure. And we can get, and using the estimated parameter, we can get on price elasticity and the cross price elasticity using this equation. And as the sum of expenditure share is equal to 1, we estimate simultaneously the 6 share functions excluding 1 for each income category or city size using the Terner's model method of Terner's seemingly unrelated regression. This table is the estimation parameter result of share functions. And this left one is by household income, and this right one is by city size. So there is 5 sets of share functions by household income, and there are 4 sets of share functions estimated parameters by city size. And the number below this one is the determination coefficient of each share functions. And this table shows the price elasticities by household income category from 2010 to 2017. And each value is average of 2010 to 2017. And this bold letter shows on price elasticities, and the others shows the cross price elasticities. For example, on price elasticity of electricity demand in category 1 is minus 0.32. And this table also shows the price elasticities by city size category, and the numbers are average of 2010 to 2017. Then bold number shows on price elasticities. And for example, the on price elasticity of electricity demand in large city is minus 0.31. And this figure shows the estimated on price elasticities by household income. This figure shows by household income, and this one is showing by energy types. And we can find that the on price elasticity of electricity, gas, kerosene, and gasoline are larger in the category 5, so in the highest income categories, than in the category 1, is the lowest income category household. So this means the higher the household income, the more elastic the demand is. So this means the energy conservation is easier in high-income households because they can afford to invest in energy-efficient appliances. And on the other hand, in the low-income household, the rise of energy prices increases household energy expenditure burdens more severely. And this figure shows the estimated on-price elasticities by city size. So this figure shows by city size, and this figure shows by energy type. So we can find that the on-price elasticities of small cities, this one, are larger than those of large cities. And because small city average house size is larger and transportation tends to depend more on automobiles because people live very sparsely. So the households in a small city have more energy appliances and automobiles. Then they have more chances to buy new appliances and cars, which are more energy efficient. And yes, in this study, as for the household heterogeneity, we focus on the household income and city size. However, there is another important heterogeneity, such as regional climate difference. And this figure shows the average monthly temperature of Kagoshima and Sapporo. And Kagoshima is in southern part of Japan, and Sapporo is northern part of Japan. So in winter season here, the temperature difference between two cities are more than 10 degrees Celsius. So the big difference. And this figure shows the expenditure share of energy consumption. And in Japan, kerosene is heavily used as a heating energy, especially in the northern part of Japan. So the energy share of expenditure consumption is there is a difference between Sapporo and Kagoshima. So the impact of differences in the regional climate on the price elasticity is one of our future research topics. And this is conclusion. The price elasticities vary according to the household income level and the size of the city where households are located. Our results suggest that energy pricing policy should be carefully designed considering the heterogeneous response of different types of households. This suggests that rise of energy price is quite regressive in the household sector. And the higher on price elasticities in the high-income households mean that energy conservation is easier in high-income households because they are affordable to invest in energy-efficient appliances. On the other hand, a lower on price elasticities in the low-income household mean that the rise of energy price increase households' energy expenditure burden more severely. The price elasticities of household in a small city are bigger than those of household in a large city because in a small city, where it's generally located in a suburban area, average house size is larger and transportation tends to depend more on automobile rather than public transportation. This implies that the household in a small city use more energy appliances and automobiles. This also suggests rising price stimulates such household to replace less energy efficient appliances with energy efficient ones. And furthermore, the impacts of differences in the regional climate on the price elasticity is one of our future research topics. So thank you very much. That's all for today. So I'm very happy to hear from you, questions and comments. Thank you very much.
Thank you very much. You also were very efficient in the use of your time. Can I, you probably said this, but the regressions that you ran, I didn't see, you may have said how many household, this is individual household data and how many households are in.
Yes, I have to say, we didn't use the survey data, original survey data itself. So because the access to the original survey data is very hard in Japan because of the privacy policy issues. So we use aggregated time series data instead. Yes.
So how many observations were in those regression shows?
Yes, the observation is from 2000 to 2000, from 2000 to 2000. So 17 observations for each categories. But we can. Yes.
So you just had, expenditure shares by income by city, and that was it,
Yeah.
right?
Yes. So, yes. And okay. Yes, and we estimated simultaneously the share functions. So 17 multiplied by 6 is our observation data. Yes. So we have freedom of degree is multiplied by 6.
So how many cities were there? So how many cities and how many? So you had, was it 5 income categories?
Yes, 5 income categories, and each categories we estimated these share functions. So okay. Yes, so we estimate 9 sets of share functions.
You have 5 income categories and you have 4 city sizes.
Yes,
groups.
Yes, that's right. Yes, yes.
Okay, so that's like 20, and then you have a time series. So you have a time series for 5 income categories in each of cities. Is that how it works?
Sorry, I can't hear you well. Please.
So we have how many? So we have 5 income categories. 5 income categories.
Yes.
4 groups of cities.
Yes, yes, that's right.
And 20 years. And how many years?
Years is 17 years.
17 years.
Yes.
So that's really the sample. It's a panel of 20 categories over 17 years.
Not the panel. We use the time series as a time series data. So we estimate separately each categories. We estimated the equation separately for each category. So but we estimated these 6 share functions simultaneously. Right. So we can get the larger freedom of degree. Then yes, that's the solution. Yes.
And it's all annual data.
Yes, annual data. Yes, yes, and preferably we want to use the original survey data. So recently, Environment Ministry published the new data that is a statistical survey on CO2 emission from the household sector that is conducted by Environmental Ministry. And recently, we are approved to access survey data. So in future study, we will try to the same kind of analysis using the original survey data. but currently we
I-
use time series data. Yes.
Okay, good. So yeah, I think if you can get the survey data and you can have data on appliances, that would be very much, probably improve things a lot, right? If you could
I
get a
think
measure of it.
Hmm?
If you could get survey data and you had
Yes.
individual households with appliances, that would help a lot. I just want to remind the audience that they can ask a question in the chat, but I was going to, while I'm waiting, in case that if they want to, but I have some other questions to ask Yuko in the meantime.
Yes.
In your graphs, you had some graphs of income and I think some prices, and they were all in yen, millions of yen. I guess my question is, so you go back, they're here. So the right-hand one, household consumption expenditure, was it back up where you were, just the previous slide?
Yeah. This one.
Is that, so that's in millions of yen?
I forgot to, yes, it's million of yen. Million of yen, yes, per annual.
Yeah, okay.
I forgot
The previous one said million of yen.
yes.
I think you should, there. That one.
Yes.
So, but you should convert those to real terms, I would think. Divide by consumer.
Yes.
Right?
Yes. But in this study, yes, I understand your question. Yes, but in this case, we want to study about the value share. So the value, so the price multiplied by volume. So expenditure itself is it has meaning. So we
in the econometrics, you had P divided by Y, so that's okay. But in these pictures, you have pictures
yes.
of nominal.
Yes, it's very. I understand. Yes, we should. Yes, because we cannot compare the nominal base. It's very difficult to compare. Yes, I understand.
Yeah.
But
yes, I think you had some price. I think you had some price pictures as well that were yen.
Yes, but unfortunately in Japan in this period, we are deflation period, long-lasting deflation period. So price didn't change at all.
Yeah, but but I think that's part of the reason it slows down. It's because when you divide by the consumer price index, the falling prices will make it not slow down anymore.
Yes.
Right. So I think I think econometrics is okay because you do it all in shares.
Yes. I understand.
But in terms of the pictures, I think you need to convert the pictures to real.
Real terms. Yes. Thank you very much.
Yeah. One other question or comment I had was on your small city versus big city.
Yes.
Another reason I think why the elasticity would be different.
Yes.
Is that so particularly for fuel use in the small city, driving time. People are driving, but driving time would be smaller probably. So if you think about the cost of driving, the cost of driving is the cost of fuel, but it's also driving time.
Driving time.
Right? Yeah, the amount of time you drive to work or school.
Distance.
So in a small city, that's going to be
very small.
Less driving. Yeah, less driving time. So a change in fuel price would actually be a bigger change in the. Well, I see that might, a big change in the cost of driving, right? Whereas in the big, whereas the big city, driving time is going to be long. So the main cost of driving is the time cost.
Time cost,
not the fuel
gasoline cost. Not the fuel cost,
not
but
the gasoline cost.
time cost. Oh, interesting.
Yeah. So therefore, you know, in the big city, a change in the gasoline cost is lower. There's a lower change in the cost of driving. Whereas in the small city, change in gasoline cost is a bigger change in the cost of driving. Because the time cost is small.
Okay.
So that might be another reason why those elasticities are different there.
Thank you very much. It's very interesting. I've never come up.
And then city gas. The
Yes,
other problem we've got.
Yes, city gas is, and in Japan, it's a little different, I think, different from the other countries. In the small city, city gas is not so developed well.
That's right. That's
So
what I was going to say.
Okay. Yes.
Yeah, so I think that's what I'm thinking. So there will be lots of households which would be zero city gas in the small city.
Gas.
Because they don't have gas on in the small city.
In Texas, in the United States.
No, in Japan. In Japan, the small city.
Yes.
Small city has no gas, right?
No
Zero
gas. Yes, no gas. Yes. Some cities, yes, doesn't have.
Yes. So I'm not sure. Let's see why. It's hard to imagine what difference that would do, but the zero, given that you've got kind of aggregate data, it's not clear. But if you go to the survey data, like you said you want to do, which I think would be good, you're going to have to take account of the fact that there's lots of zero.
Yes.
There's lots of zero consumption in the small town cities. Zero for gas.
So it would be better to aggregate the city gas and liquid petroleum gas.
Maybe.
Maybe. Yeah.
Maybe.
I'll try. Yes. Yes.
Yeah. And kerosene, the other one I was thinking, but because it's annual data, it probably doesn't matter. But you know, in most countries, overall energy demand is very sensitive to weather. Like you said, you showed the picture of Sapporo and
it's very
Fukushima.
Big point. Yes, I think so. So
Yeah. So if you have any data that's not annual, but maybe even annual, putting the weather variable in the regressions as a shift variable might be important.
Shift variable, yes.
Just like you have income. And it may be, like colder years, you have more energy demand, and warmer years less so. And maybe having a weather variable would be very important, like you said. Let's see. And you can't, you had transportation costs, but you couldn't separate out necessarily use of public transport, could you? Very well. Because it included taxi and other things, right?
Yes. We include.
So you can't get public transport also.
Transportation expense. All of the transportation services include. Yes.
Yeah. So can you just get railroad, for example?
Yes, it's possible to divide.
I mean, an interesting substitution would be between car use, which is gasoline, and railroad, which is public transport.
I can't get your point.
So it would be interesting to see the cross elasticity between gasoline and railroad.
Yes.
Car versus
in order to get the precious price elasticity, yes, we should choose more, targeted to, railroad and gasoline, yes.
Mm-hmm. Mm-hmm. Okay. Let's see. That seemed to be main. Oh yes. One other last thing I have. As you said, part of the elasticity response might be a change in equipment. People switch to more energy appliances.
Yes. We said, yeah.
But you might expect that to be longer run and the use to be shorter run.
Yes.
Can you allow for dynamic response? You know, so
yes.
the price change affects the lag. Price change affects.
Yes. In this analysis, we don't introduce lag structure. So yes,
No.
the plus elasticity is just a short-term elasticity. So yes,
Yes.
very good point. And if we consider
I think some of your
yeah.
I think some of your pictures may have suggested a lagged effect.
Lag effect, yes, it's very important. Thank you very much.
And let's see, in your actual estimation,
yes,
as well as these 1, 2, 3, 4, 5, 6, you have 6 energy commodities, right?
Yes, yes.
Then, and then the omitted category is all other expenditure. That's right.
Yes, yes. Omitted or the residual, as we treat it as a residuals. So 1 minus. Yes.
Yes. Yes. So it's almost like I imagine if you think about your theory, your indirect utility function, I wonder if implicitly there are assumptions about separability between energy use and other consumption.
Yeah.
Is that kind of built into this analysis, that energy consumption is kind of separable?
Okay, separable. Yes, it's very good. Yes, important things. So,
you might think about.
yes.
If there's something there. Okay, if there's no, I don't have any other. I guess we don't have any other questions in the chat. I think I've just about. Run out of my questions. I guess you can't get data. Other variables, given you have time series, it might be good to see if there are other things, other time variables you could have, like average fuel efficiency of vehicles, or number of appliances, or there may be other data you could get.
Yes.
Like that. May be important.
Interesting. Yes.
Okay. If there's no other questions from anyone else, I think that they were all my questions.
Thank you very much. It's very valuable questions. Thank you very much.
Okay, good. Thank you. Okay. So that, in fact, we might move on to our next speaker, which our next speaker, who is Hayato Nakata, and he's going to talk about oil prices, exchange rates, and stock market returns.
Okay. Is it okay? No?
Yes, that's very good. Yeah, I can see your slides very well.
Thank you very much. Thank you, Peter. I'm Hayato Nakata from Meisei University, Japan. Today, I'm going to present a paper titled Oil Price Exchange Rate and Japanese Stock Returns. It's a joint work with Tokuo, Iwaisako, and Kohei, Aono. So let me start my presentation. So I'd like to explain purpose of this paper. Japan is a major energy importer, and oil price fluctuations can have large impacts on Japanese macroeconomy, so that on Japanese stock returns. On the other hand, Japanese economy heavily depends on its exports. So FX rate change do have large impacts on Japanese stock returns too. And Japan's exchange rate is also affected by oil price changes. Furthermore, needless to say, different factors move oil price. For example, supply factor and demand factor, speculation factor, etc. So we need identification strategy to identify structural shocks to explain oil price. So in this paper, we want to analyze the impacts of oil price and FX rate fluctuation to Japanese stock market in a unified empirical framework. Okay. Next, let's look at model structure and the data of our paper. This figure shows a relationship between our approach and the previous studies. Recently, Killian and Park and Reddy analyzed the impact of oil price on stock returns. On the other hand, Aono and Noden investigate co-integration relationship between oil price and exchange rate. Furthermore, Chen, Roche, and Rogoff try to use exchange rate of commodity exporter to predict commodity price. At last, many papers on Japanese stock market focus on the impact of exchange rate on Japanese stock returns. So the novelty of our paper, our approach, is that it includes these three variables in a unified empirical framework. Doing so, we consider exchange rate as endogenous variables affected by oil price. In this paper, we employ two identification strategies. First strategy is developed by Lutz, Killian, and Park. And we extend this framework by adding exchange rate. So we call it extended Killian model. Following this strategy, we identify these four structural shocks. Second strategy is developed by Robert Reddy. We also extend this framework by adding exchange rate. We call it extended Reddy model. In this case, we identify these four structural shocks. Next. Our empirical strategy is based on this two-step estimation. In first step, we estimate VAR, including oil and FX, to tabulate structural shocks series. In second step, we use structural shock from first step as exogenous variables to estimate VAR, including stock returns. And this is a variable and structural shock in the extended Kilian model. Variables include growth rate of oil production and proxy for global real economic activity and oil price and real effective exchange rate. And as for global real economic activity, let's Kilian construct these variables using the data on shipping freight. And structural shock include four shock: oil supply shock, aggregate demand shock, oil market specific demand shock, and pure exchange rate shock. And this is our structural VAR. Upper equation is Kilian's three variables VAR system. And lower equation is our four variables VAR system. Shocks are recursively identified in this system. This identification is justified by theoretical assumption. So this is the variables and structural shocks in the extended ready model. As for this model, variables include four variables: crude oil price change, stock price of oil company and VIX, and real effective exchange rate. And structural shock include four shock: oil supply shock, aggregate demand shock, risk shock, and pure exchange rate shock. This is our VAR. Upper equation is ladies VAR, and lower equation is our four variables VAR. In this case, also shocks identified recursively, but these two models are based on different theoretical assumptions. This slide summarizes our data set. K means Kilian model includes these variables. On the other hand, R means that ready model includes these variables. So let me move on to the empirical results. First of all, we regress stock returns on oil price and exchange rate. So yen appreciation value has significant impact on Japanese stock returns. And oil price increase alone has positive but insignificant impacts. On the other hand, oil increase has positive and significant impact in the estimation, including both oil and FX. Next, we regress stock returns on same month's structural shocks. In case of Kilian type shock, oil price and exchange rate shock have a significant effect. On the other hand, in case of ladies type shocks, demand shock, big shock, and effect shock is significant. In terms of model performance, Lady's model is much better than Kilian's model. We skipped. So this table shows correlations of both types structural shocks. Correlation between surprise shocks are almost zero. On the other hand, correlation of Kilian's oil price shock and Lady's surprise shocks are positive and high. And correlation between FX shocks are also positive and high. At last, we estimate Bernanke-Katona type VAR with structural shocks. This is Bernanke-Katona type VAR. The endogenous variables of Bernanke-Katona type VAR include stock return and monetary policy variables. And it's almost the same as, in regard to model performance, Lady's model is much better than Kilian's model. It's almost same as previous estimation. In regard to monetary policy variables, adding such variables improves the explanatory power. So let me move on to our conclusion. In this paper, we construct a structural shock series behind the oil price and exchange rate fluctuations using Kilian-Park and Lady's identification assumptions. So we use them to explain Japanese stock returns. So we find Lady's structural shock series have more explanatory power. But it's not so surprising since current stock return of US energy sector are included in the regression or VAR. In both framework, one structural shock contain residual or garbage leaving unexplained by other factors. Such a shock is oil market specific demand shock in Kilian's framework and oil supply shocks in Lady's framework. Former have positive effects and latter have a negative effect. But their correlations are high. So we have to be careful about economic interpretations of our empirical result. As future research, we need to explore data specification and macro factors for Japanese stock market. And thank you for your attention and comments and welcome.
Thank you very
That's all.
much. Thank you. Again, I remind anyone in the audience, you're quite welcome to ask a question by typing in the chat, but apparently you can also turn on your own mics and ask a question orally. In the meantime, we don't have anyone. We have one. Yes, I have a question from the audience. Go ahead, please.
Hello, can you hear me?
Yes.
A good presentation, and I have two minor questions. So have you done the seasonal adjustment for your monthly data? And what lag are you using? Thank you.
So, Mr. Hayato, can you-
Okay. We use monthly data from 2000 to 2019. Okay.
Yeah, I mean, have you done the seasonal adjustment? Because crude oil price might change very seasonally.
Oil price?
No,
Yeah,
see, yeah, the seasonal adjustment, I think. Did you do seasonal
Yeah.
adjustment?
yeah, that's right.
Is the question. No answer? You know, if it's seasonally adjusted or not? I'm not sure. I mean, the original series might have been seasonally adjusted, right? Or like I don't know. Probably, I don't know. The main one would be the growth rate of world oil production. I don't know, I suppose that's probably raw. I suspect there's no.
In this paper, we use IMF data, IMF primary commodity price statistics. This data include WTI, North Sea Brent, and Dubai.
Right. And you deflate by the US CPI, you're saying there, right?
Yes. We follow Kilian's paper in this respect.
Yeah. Because that was one of my questions, to make sure it was the that you were using real oil prices, but you're doing it in commodity prices
yes,
are in US dollars, and then you deflating by the US CPI, right?
Yes, I understand your question. It's an important problem. We did a robustness check. We use real data and nominal data, but difference is not large. Almost the same results. Okay.
You should be using real, I think. I have a question. With the Japanese economy,
yeah,
I would think LNG price will be very important because it affects electricity prices, right? And maybe even electricity price.
Yeah.
But rather than the oil price or as well as the oil price. Did you look at either electricity or gas prices?
For Japanese economy, oil price is a more important problem after large earthquake and accident of Fukushima.
Okay, I mean, it might be interesting to look at the gas price or electricity price too.
Gas price, yes.
Yeah. I have a couple of other questions. The stock prices that you have here, you've got to hear the global stock price index, global energy production companies. They're the IOCs, right? The major IOCs, or and then for your other stock variable that you're interested in the second step is Japanese stock prices. Is that right?
Yeah.
I would think that the Japanese stock prices, you might like to distinguish some firms that use energy from firms that, well, I don't know, supply, I suppose.
It's it's also
Stock returns. What I'm getting at is which stock returns do you have in item 2 here? You got structural stock shocks from first step to estimated VR, including stock returns. Is that just the Japanese stock price index, or can you split that into different industries?
I see. First of all, index of oil producing firms, all US or other international company, not including Japanese company.
Okay.
We follow Ladies' approach, and Lady tried to explain US stock market. So it's a serious problem of our approach. And we need to more better specification. You see.
Okay. And then in your Japanese, when you looked at the second round, you had the structural shocks here affecting Japanese stock prices, right?
Yeah.
Is that just the Japanese stock price index, or can you look at different companies there? Because the sensitivity might be different for industrial, so different kinds of companies, you know, like financial and industrial and so on.
In Japan, there is no large energy companies. So
INPEX, right?
yeah.
What about the electric utilities? TEPCO.
It's important problem, yeah.
INPEX and TEPCO are probably going to be affected differently than a bank.
I see.
Right.
Maybe a Japanese investor focus on stock of automobile companies or exposed.
Yes. Yes. Automobile companies would be different. Yeah. They'd be different from banks and, for example, financial companies or and even utilities, or like I said, or INPEX, so presumably is different. It's
yes.
And gas companies may be different. I mean, it'd be interesting to look at. It would add more credibility to your model to separate out, I think. The other question, I guess, is methodological.
Yeah.
And this is because of you're following Reddy, but why not include the Japanese stock prices and so forth in the original VAR? Why separate it out into 2 steps? Why do they do that? You could just You could just.
Oh, okay. We employ two-step approach following original Kilian's approach. Kilian explained the impact of oil price on GDP using two-step approach, and we follow this methodology.
Okay. Do you know why what justified doing two-step? Did he provide a justification for that? I presume he did, but then the question is, does his justification work in your context?
Mm-hmm.
You might want to give that some thought, I guess. What about Reddy? Did Reddy have a two-step procedure too?
No. Just a moment. Okay, Lady employs a two-step approach too.
Yeah, okay.
But it's better to employ unified one-step approach. I understand. But
I'm not sure. I'd like to know.
It's hard to find the appropriate specification.
Okay. Okay. Maybe at this point, if there's any more questions for Hayato? And if not, I guess, are there any questions for any of the other speakers? Do we have any? I can open it up to any questions for anyone. The speakers can ask each other questions if they like. Okay. If we don't have any more questions, I guess it leaves me. I'd like to thank all the three speakers. You did a very good job of presenting your work, and you did a good job staying on time. Thank you very much. And I hope you got some benefit from your participation in the IAEE conference, and we hope to see you at future conferences. And thank you very much for presenting your work. And it's a great, I think it's a good thing for you all to do. Present your work before you send it off to the journal to get refereed. So thank you very much. And thank you very much to the audience for turning up to our session. And if there's no more questions, we'll stop it at this stage. So thank you very much.
Thank you, Peter. Thank you, Felipe.
Yes.